Can you hear me all right? Dr. Pishattivar, can you hear me all right?
Yes,
Can you hear me all right?
yes. You are audible. You are audible.
Perfect. Let me share my screen and
Okay, okay.
can
One.
to see if the slides are moving through. Right. Do you see the slides moving?
Yes. It is visible.
Perfect.
Uh, shall we start?
Sure,
Dr.
I'm
Shashwat,
ready.
shall we start?
Sure, I'm ready. Should I go ahead and share my screen?
Just wait. Shweta will share the screen. After that, she will give access to you.
Sure.
Good afternoon, one and all. I, Dr. Shweta Dhonse, welcome you all for this afternoon session on the topic Engineering Ultra-Wide Bandgap Semiconductors at Atomic Scale by Dr. Shashwat Ratkantiwar. Dr. Shashwat Ratkantiwar is a seasoned material scientist with over a decade of expertise in Group 3 nitride semiconductors. His groundbreaking approach integrates semiconductor material science, physics, and electronics, envisioning revolutionary advancements in electronic, optical, quantum, and critical device technologies. Dr. Ratkantiwar earned his undergraduate degree in metallurgical and materials engineering from Visvesvaraya National Institute of Technology, Nagpur, India, shifting gears to nanoscience and engineering for his doctorate at the prestigious IISc Bangalore. This was followed by his postdoctoral tenure at North Carolina State University's Wide Bandgap Laboratory. He is currently the director of MOCVD research at Lit Thinking Ultrawide Bandgap Research Center, based in Orlando, Florida, where he spearheads the research on metal organic chemical vapor deposition of ultra-wide bandgap nitride semiconductors, enabling far ultraviolet optoelectronics and KV class power electronics. With 31 journal publications, 80 international conference presentations, 1 patent, and over 15 invited talks, Dr. Kantiwar's contribution have garnered editors' pick selections in applied physics letters, alongside numerous awards and recognitions for research excellence, including Best Oral and Poster Presentations. Dr. Shashwat serves as an independent reviewer for 14 major journals and also chairs technical sessions at esteemed conferences such as American Conference on Crystal Growth and Epitaxy Compound Semiconductor Week, Electronic Materials Conference, and Materials Research Society meeting. We are very delighted to have such young scientist with so many feathers in his cap. I welcome you, sir, for this session.
Thanks for that kind introduction.
And I request you to now deliberate your speech to the audience. Thank you.
All right. Can you see my screen all right?
Yes, yes.
You also see my cursor moving?
Yes, yes.
Perfect. All right, I'll get started. Thanks again for that kind introduction. Hello, everyone. Thanks for joining in for my seminar. I extend my gratitude to the organizing committee for this exciting opportunity. I'm honored to be here today and very excited to share with you all about my research on a class of materials known as wide bandgap semiconductors. Before I delve into my research, I'll give a quick background on my journey so far. A bit of it was covered already. So I earned my undergraduate degree in metallurgical and materials engineering from Visvesvaraya National Institute of Technology in Nagpur. After that, I switched gears to this exciting field of nanoscience and engineering, in which I pursued my PhD at the Indian Institute of Science in Bangalore. Following that, I had a brief stint at IISc as a research associate, and then I moved to the US for my postdoctoral tenure with the Wide Bandgaps Laboratory at North Carolina State University. And from January this year, I have been directing a research division at a startup research center, Lit Thinking Semiconductor Research Center. I'll discuss more about what we do here toward the later half of today's presentation. So yes, Lit Thinking is based out of University of Central Florida's campus here in Orlando. It's a nice, beautiful campus. So if you happen to be around the area, please ping me and I'll be happy to show you around. All right, so with that, let me move to the topic of today's presentation, where I'll be very excited to share with you about my vision of using this class of materials known as wide bandgap semiconductors, and how I have an expertise in engineering these wide bandgap semiconductor materials at the atomic scale. So you did hear me right. I'm going to show you today how I engineer or how I tailor these materials at the atomic scale, and how I believe this will open a pathway to next generation electronic device technologies. So here's the outline of today's presentation. I'll start by giving a brief background on what semiconductors are and then what are wide bandgap semiconductors. Then I'll delve into how do we synthesize these semiconductors and how do we control defects in these semiconductors at the atomic scale. Then I'll talk about how I have tried to act as a nexus between the fields of material science, electrical engineering, and physics. How I use an integrated approach to connect these fields, and how I use this nexus to develop next generation device technology. So I started as a material scientist, right? I did my undergrad in material science, and then I taught myself electrical engineering and physics during my PhD to sort of act as a nexus between these fields, and look at these device technologies from different lenses or perspectives. So this has allowed me to work on nice technologies that I'll be sharing with you today. So I'll discuss about how I use these materials in power electronics, optoelectronics, quantum computing, and so on. And finally, I'll summarize this presentation. So let's start with the basics, right? So we all lived in this exciting era of a rapidly evolving electronics field, right? Uh, so the investment in research and development of semiconductors has been proliferating as we speak. So at the heart of every semiconductor device, be it used in power electronics, optoelectronics, radio frequency electronics, microelectronics, or what have you, is a meticulously engineered semiconductor material system. So what exactly are semiconductors? So as the name suggests, semiconductors have conductivity not as low as insulators like glass or plastic, but also not as high as metals. Right? Metals have a large conductivity, as you can see from this plot here, and insulators have about 20 orders of magnitude lower conductivity. So semiconductors lie in between. So why is this so? So to understand this, we go back to our high school physics picture, where we utilize this concept of something known as energy band gap that helps us understand different classes of materials. So to the left here, I have insulator, where we see valence band, which consists of fully occupied electrons, right? So this is the outermost uh, band of the material, which is fully occupied with electrons. And conduction band consists of the lowermost unoccupied band in the material. So, so the gap between these two constitutes the band gap of a material. So in insulators, it so happens that this band gap is large. So it is several electron volts in number. So just to give you a context, our room temperature thermal energy is 26 milli electron volts. So the band gap in insulators is orders of magnitude higher than the room temperature thermal energy. So what that means is that you cannot conduct any charges in an insulator. This is because valence band is fully occupied by electrons. So electrons do not have any state to jump to, and therefore there cannot be any conduction in the valence band. And there are no carriers in the conduction band whatsoever. So insulators do not conduct any electricity uh, as such. Now, if you look at conductors, this is where the conduction and valence bands merge together. So you have excess electrons and you also have available states to conduct, and that's why conductors conduct a lot of electricity. So now semiconductors lie in between, such that you do have a finite band gap, but this band gap is relatively small, such that you can now excite carriers from valence band to conduction band. So in this process, you create electrons in the conduction band and holes in the valence band. So you can conduct using either of them. So, so this is what makes semiconductors different than insulators and conductors. But what makes it unique is that you can tune the conductivity of semiconductors by orders of magnitude, as you can see here. So we do this by intentionally doping the material, where the idea is that, let's say we start with silicon, which is a group 4 element, right? In our periodic table, silicon is a group 4 element. So in a normal configuration, all your valency is satisfied in silicon lattice. So what you do in this process of doping is that you either choose a group 5 element, such as phosphorus, or a group 3 element, let's say a boron. So when you choose phosphorus, you have an excess electron in the lattice, right? Because phosphorus is a group 5 element. So what this leads to is this excess electron that is available in the lattice for conduction. So it's as simple as that. If you use boron, you have one deficient electron, which is known as a hole, and you can use that for conduction in the lattice. So that if you use phosphorus, it's known as N-type semiconductor because you have excess electrons, and in a P-type silicon, you have excess holes in the lattice. So essentially, by changing the dopant concentration, you can change the conductivity or inverse of resistivity by orders of magnitude, as you can see in this plot. So from here, we can understand that these atomic level defects play a fundamental role in controlling the properties of semiconductors. So this was all about electrical properties, right? So now let's look at optical properties. We start with sapphire. So sapphire is a wide bandgap semiconductor. So it is transparent to light, right? As you can see here. So if you have a completely defect-free sapphire, uh, it would look like this. But you would argue that you see sapphire in all these colors, right? Sapphire is used as a jewel, use it in jewelry. So what if I were to tell you that it's all sapphire, all of these crystals are sapphire. The only distinction is that each of these have different point defects in the material. So point defects, even when present in small numbers, can change the properties of these materials drastically. For example, let's again look at the bottom left plot here. So when we talk about 10 to the 16 per centimeter cube of dopant concentration, we are talking about parts per billion level, right? In 1 mole of any solid, you have 10 to the 23 atoms. And if you take a billionth of that is about 10 to the 15 to 10 to the 16. So even one atom in billion atoms, if you swap it with another element, it completely changes the properties of semiconductor, right? Similarly, optical properties also get influenced significantly by controlling these defects in the material. So essentially, I find defects to be rather beautiful, right? So I think I very much agree with all these great people here. Sir Charles Frank had a quote that people are like crystals. It's actually the defects in them that make them interesting. Because if you have a perfect crystal, it would be dull because there's only one way to get a perfect crystal, but there are infinite ways to make a crystal defective. So this is what makes defects in semiconductors to be an enticing field to work with. All right. So, so we all know about silicon, right? We use silicon in our common day-to-day digital and analog electronics, right? All our computing is using silicon. A lot of electronics around us is all based out of silicon. So silicon is the most traditional semiconductor out there. And then we also have gallium arsenide as one of the important semiconductors, again, a traditional semiconductor that has been employed in optoelectronics, high frequency electronics, all your 4G sort of towers, base stations were based out of gallium arsenide. But then there is a new generation of semiconductors where you see that the band gap of these materials is rather high. So these are known as wide bandgap semiconductors, and aluminum nitride here is known as ultra wide bandgap semiconductor. So now, if you go back to the picture of bandgap which we looked at, where I mentioned that the room temperature thermal energy is only 26 millielectron volts, so which is like a percent of this bandgap, then you would tell me that wow, these materials shouldn't ideally qualify as semiconductors, but rather they should be insulators. So that was indeed true. For many years, these semiconductors were deemed as insulators, but not until lately, where people have been able to dope these semiconductors. And I specifically work on the highlighted region here, which is gallium nitride and aluminum nitride. We call these materials as group 3 nitrides because you have group 3 metals, gallium and aluminum, and you have nitride of these metals. So the tight binding of these elements leads to a wide band gap in these materials, and as we'll see later, this wide band gap makes these materials exceptionally useful for these high frequency, high power electronics and UV visible optoelectronics. So you see a gallium nitride to be already employed in your fast chargers. You have gallium nitride in your 5G base stations and 6G base stations. So in Internet of Things, gallium nitride is playing a significant role, as we'll be uh, learning in just a bit. So, so remember I mentioned that, okay, if you take a silicon lattice, you can dope this by using, let's say, a group 5 element or a group 3 element. So essentially what happens is in an undoped semiconductor, you have Fermi level, which is the average energy of electrons in semiconductors at the mid gap. Now, when you dope the semiconductor, what happens is that you create these energy states which are close to the conduction band. And now these are sufficiently close such that at room temperature, you excite enough carriers so that your Fermi level also moves close to conduction band. And this is how we achieve conductivity in silicon. Now, in wide bandgap materials, what happens is that the material does not like to get doped at all. So what it will do as a response to doping is to incorporate some intrinsic defects, such as these, which now trap your electrons back and move the Fermi level back to where it started. So this is what makes doping in wide bandgap semiconductors a formidable challenge. And this is why it was so difficult to even dope these materials to modest levels. So So the modern definition of wide bandgap semiconductors is, in addition to it having a wide bandgap, it is only useful if you can dope the material, right? So this is what the art is, and this is what I'm an expert at, as I'll be discussing in just a bit. Uh, so, so the question comes is that how do we go about synthesizing these semiconductors, right? And I mentioned that these defects play a fundamental role in controlling the properties of semiconductors. So I mentioned about this defect that you see in top right here of this cartoon, where we are substituting uh, a foreign atom in the host lattice. So this is known as doping, but it need not go on that site all the time. It can go in a site where we do not want. We can also knock out an atom from its site, which is called a vacancy. So there can be a zoo of defects that you create in the material, and each of these defects has a profound impact on the material properties. So the question is, for all these next generation device technologies, can we really engineer these defects at those parts per billion scales that we talked about previously? So that is the art here, and we synthesize these semiconductors by a host of techniques. But what I prefer to do it with is something known as metal organic chemical vapor deposition. So one of these reactors I've shown here on the top right. This is housed at IISc Bangalore. So this equipment is quite complicated. As soon as you open these cabinets, you understand that there are many gas lines involved, and this is the reaction chamber. So you have these tons of lines coming in, delivering all these precursor gases and so on. So it's quite a complicated process, but you need such a process to really ideally synthesize these semiconductors one atomic layer at a time. So we synthesize these semiconductors one atomic layer by one atomic layer. This is how precise control we have over the synthesis. And the question again is, how can we control these defects at parts per billion scales, right? So to grapple with this formidable challenge, in the last 10 years, I've worked hard toward developing predictive approaches for systematic management of these point defects by drawing on tools and concepts from thermodynamics and kinetics. My colleagues here from materials or mechanical engineering would resonate with me here. So this is all chemistry, physics, and material science all done together. So you make predictive approaches where you use these individual knobs very nicely to control the gas chemistry, and you make these reactions happen at elevated temperatures upwards of 1000 to 1400 degrees Celsius. So this is insanely large temperature, and you need to exert big control on this growth process for the desired outcome. So I won't go into a lot of technical details today, as our audience is broad, but this is what I would like you to drive away, that even though these semiconductors are nanometer scale, you need these huge equipments to synthesize these semiconductors reliably. All right. So this brings me to my research philosophy, right? I told you that these defects have a profound impact on material properties, which in turn governs your device performance. So I've tried to sort of adopt this command philosophy where it's acronym for understanding correlation of materials micro and nanostructure. So what it means is that I understand how defects manifest in the material, and I correlate that to material properties, which in turn correlates to device performance. And understanding this over encompassing correlation is critical to make next generation electronic devices. So essentially, I work at the intersection of these all fields in an integrated approach to sort of develop these next generation device technologies. Uh, so so let me first talk about how we use such kind of defect control to develop next generation power electronic devices. So before I delve into that, let me talk about what power electronics is. So power electronics, in essence, is any process in which you convert the power. So the conversion of power can be, let's say, from AC to DC, can be a step up or step down in voltage, or so on. So let's take an example of you charging your cell phone. So what you have at the wall plug is, let's say, 220 volts if you're in India, 110 volts if you are in the US, and then either of these two, depending on where you are joining us today from. So you have this as alternating current, right? What we get from the electric grid is alternating current, AC. But what we need for charging our cell phone is a direct current, so DC. And also, our cell phone batteries are only rated to take, let's say, about 10 to 20. So what your charger does is that it first converts it from AC to DC and then steps down the voltage. So this is one example of power electronics. We have such conversion happening all around us, right? In every system, be it solar, be it wind energy conversion to give you back to the grid, be it electric trains, and so on. Everything around us deals with power electronics. So if you see the evolution of power semiconductor devices, it all started at or 1950 with the first invention of a transistor, right? And this was based out of germanium. So germanium was researched intensely for about 10 years. And then as soon as we saw the onset of silicon technology, it just outpowered germanium, and germanium technology just dwindled off in the mid 60s, and the silicon technology took off. And then we developed thyristors, we developed MOSFETs, which are a kind of field effect transistors, and so on. And then with the advent of gallium arsenide, we developed the radio frequency technology in the 75 to 80 period, and it went on. And now this radio frequency and power electronics seems to be taken by these wide bandgap materials, which are, let's say, silicon carbide, gallium nitride, and so on. So this is sort of the historical perspective of power semiconductor devices around us. All these devices are something you interact with day in and day out without necessarily understanding what goes in there. Uh, but uh, but now let's look at the reason why these new generation semiconductors came in and are trying to replace the incumbent technology based out of silicon and gallium arsenide. So to understand this, let's look at some material properties. For any semiconductor, some of so these are some important properties that one needs to consider. So the first is electron mobility, right? So electron mobility is sort of the acceleration with which you can, or the acceleration you can achieve uh, for carriers, let's say electrons in a semiconductor, by applying an electric field. What is electric field? It's a potential. So if you apply a potential to a semiconductor, electron mobility tells you how fast do your electrons accelerate in that electric field. So it's an important parameter. We want this to be as high as possible for conducting large amounts of current. So similarly, band gap is very important, right? Gallium nitride has about 3 times larger band gap as compared to silicon. Now, what the band gap translates to typically is a critical electric field or breakdown electric field. So this gives you an idea of how much field a unit thickness of a semiconductor can sustain. So let's say that you have about 1 micron of a semiconductor. So 1 micrometer is 10 to the minus 6 meters. So if you have that sort of material, and if you're trying to drop electric field across it, so this parameter, this property tells you how much field can you apply before the semiconductor breaks down. So you see that because of a wider band gap, gallium nitride has about an order of magnitude higher critical electric field. So what these properties translate to is a better uh, figure of merit. So this figure of merit is for a power device. Again, I'm taking an example of a power switch. So in a power switch, like we talked about, a charger, let's say your phone charger, there are two states. One is when you are charging your phone. So let's call this as an on state. So in the on state, the idea of the switch is that it should exert or exhibit least amount of resistance, right? So that you can pass as much current through the power switch as possible without losing a lot of power. And in its off state, when you don't want to charge your phone, you want the charger to block a certain amount of voltage. So it's called as off state. So in the off state, the breakdown voltage comes in important, and in the on state, your on resistance becomes important. So all of this translates to a linear dependence of this figure of merit on the mobility and a cube dependence on the critical electric field. So essentially, because of an order of magnitude higher critical electric field and about twice mobility, gallium nitride has a much better figure of merit compared to silicon. So what this means physically is that for the same rating or for the same breakdown voltage, your gallium nitride device can be 15 times thinner than a silicon device and can accommodate about 250 times higher doping density, which means that it will have a much lower on resistance for the same breakdown voltage. So this is the reason why your new generation chargers are only this small, right? So my charger here, the one I'm using for charging my laptop, is only this big, and my previous laptop charger used to be yay big. So not only has this shrunk in size, it also packs more power density now, and it's also more efficient. You would find the new generation chargers to heat up quite less. So this is all because of gallium nitride being implemented in your chargers. So now imagine if you could use gallium nitride in not just power chargers, but in all technologies around you. So there are all these technologies depending on your current rating and blocking voltage rating, you can use power devices in, and all of these can significantly improve if we were to replace the incumbent silicon technology with gallium nitride. So obviously the main application, it all started with Oppo, which is a Chinese mobile company, opting for gallium nitride in their chargers. This was back in 2018, and I remember of buying this cell phone from Realme, which was the first fast charger back in those days when I used to be in India. So it all started from there, and then we saw adoption from many companies, and now even Samsung and Apple is moving in with gallium nitride based technology. So we are already seeing close to $1 billion market just for the fast chargers in this technology. So it's a huge market. Another market for gallium nitride based power devices is in electric vehicles. So not only do you need it for your traction inverter and the DC-DC converter, but you can use gallium nitride based transistors in almost all power electronic elements in your car. If not all, but I would think majority can ideally be swapped with gallium nitride based transistors. So we saw that in 2018, only the consumer market dominated for gallium nitride, with like Oppo, Samsung, Realme using this technology. Then we predict now sometime around next year, automotive market would also go up, and then eventually we predict that industrial market will also take off for gallium nitride based devices, and this would be for kilovolt class devices, right? So these would be rated for more than 1,000 volts. So this is in huge industries where you want to convert large amounts of power. So this is where gallium nitride will eventually go, and this is a sort of pictorial representation of what I talked about. So about 70% compounded annual growth rate was already seen in this technology. So this is growing rapidly. It's already close to $1 billion industry right now, and there's also a lot of growth in defense and aerospace sector, which is coming up. So we have huge programs here in the US where defense and Air Force laboratories are funding our research for developing this technology. So essentially, we saw the first gallium nitride device in 2010, and it has been quite a progress from that. And we already have seen the use in data centers and in electric vehicles. Tesla is currently using silicon carbide, but it is also planning to move to research on gallium nitride for the devices as well. And other electric vehicles are also moving into gallium nitride. So essentially, every big company is moving from the traditional silicon technology to these wide bandgap semiconductors. So having discussed all these applications, I just wanted to give you a gist of how do we go about designing these devices. So the next generation technology is going to be in kilovolt class devices, where these devices would be rated for several thousands of volts. So So when we talk about these power devices, till now I only talked about, let's say, this slab of semiconductor that you want to use for power devices, but you just cannot use one slab of material. You need to engineer different elements in it. So, so the main meat of this, the main workhorse for a power switch is something known as a drift layer that I've shown here. So this is what will sustain your electric field in the reverse bias, and this will be also the layer which will help conduct large amounts of current in the on state of a power switch. So so let's say that you want to so you connect uh, anode on the top, cathode on the bottom. So you connect cathode to N plus gallium nitride substrate. So this is highly doped gallium nitride, which would have high conductivity, but you cannot use N plus gallium nitride to block voltage, right? What happens if you block, let's say, if you apply electric field to a metal, it cannot sustain anything. So that's what happens to N plus gallium nitride. So it's only used to make a bottom contact, but your workhorse remains this lightly doped gallium nitride layer. So the way this works is that when you apply electric field to this material, the way it would drop is like this. The peak of the electric field would be at the surface, and then it will reduce down as you move towards the depth of the semiconductor. So the way this will vary with the depth of the semiconductor will depend on its doping. So lower the doping, shallower would be the slope. Higher the doping, steeper would be the slope. So the area of this triangle determines your breakdown voltage. So you are integrating electric field over distance, and integration of electric field over distance gives you voltage. So how do you increase the breakdown voltage, right? So one way to do it is by reducing your doping, which will make the slope shallower and basically increasing your thickness of the drift layer. So this is what I have pictorially shown here. For a given breakdown voltage, for a higher breakdown voltage, one needs to increase the drift layer thickness and decrease the doping concentration to accommodate for high breakdown voltage. So you can already see that at let's say 2 kilovolt, we need doping concentration of the order of 10 to the 16 per centimeter cube, which is parts per billion in that semiconductor. So this needs to be done in a precise manner for this technology to work. So it's very sensitive as such to the synthesis technique that we use. So if you look at the trade-off between on resistance and doping, so you see that when you reduce the doping and increase the thickness to increase your breakdown voltage, it always also increases on resistance. So there's always this trade-off that you work with. So we worked on this technology for many years, and I'm going to show you the final result of our technology. We got this project uh, from the Department of Defense here in the US. So we eventually delivered this product where our on resistance versus breakdown voltage, you can see here that we delivered a device which was one of the best devices out there, which had for a given breakdown voltage one of the least on resistances. So much so that the devices are already close to the silicon carbide theoretical limit. So silicon carbide is the existing technology right now, and even our prototype devices seem to be working quite optimally. So that it shows a huge potential um, uh, to replace the already developed silicon carbide technology. So in a sense, I wanted to drive across this point that by carefully understanding the defects in these materials, so looking at things from a material science perspective, uh, electrical engineering perspective, we talked about electric field management, which comes in the canvas of electrical engineering. And by understanding how the current flows in the material, how the electrons move around in the material, which is physics. By understanding all of this, you can cater to these next generation devices. So obviously this is a future technology, and we'll soon see these out in the market. But what is beyond this, right? So the theme of this conference is what is going to be in the next couple of decades. So I envision aluminum nitride to take over gallium nitride. So remember, uh, aluminum nitride has a wider band gap, right? So it has 6.1 electron volt, and this helps aluminum nitride to have a 5 times higher critical electric field as compared to GaN, and about 50 times higher critical electric field as compared to silicon. So even though the electron mobility is a tad bit low in aluminum nitride, the figure of merit still translates to a much higher value because of the cube dependence on the critical electric field. What that means is that aluminum nitride based devices would can be potentially much smaller and more efficient. So essentially, if we can realize aluminum nitride, this will lead to disruptive technological changes with unprecedented device performance. For instance, like the gallium nitride chargers that we see can be made as small of a footprint that they can be completely accommodated in your laptop, and what you would only need to connect is a cable to charge your laptop. Wouldn't that be cool? So I feel that aluminum nitride technology has a long way to go because of the complications in doping this material, but we have had exciting results on this front. In the interest of time, I would not be showing those results, but yes, we have been able to dope these materials reliably now, and these materials are no longer insulators, but can actually be used as semiconductors. For example, we developed these aluminum nitride power diodes. Here the important thing is the ideality factor in these devices. So this should be close to 1, and the previous best value out there in the literature was 5. This is how difficult it is to make power devices based on aluminum nitride, and we were able to show values which are close to ideal, with a near ideal turn on voltage, and we were able to pass 1 kilo amperes of current per centimeter square of the footprint. So this is a very good value, 3 orders of magnitude higher than the best reports out there. So this really testify that our aluminum nitride is conducting in its on state. And if you look at the off state, we only using 1 micron aluminum nitride, we could lock about 700 volts, which translates to 12 megavolt per centimeter electric field. And this was done without any dedicated field management. So this only uh, uh, underscores the performance of aluminum nitride based technology. So these are very exciting results, and we'll be publishing this very soon. So this was all about power electronics and where I see this field to progress moving forward. This With this, I moved to the second application space I wanted to share with you today, and this is known as optoelectronics. So this is essentially all optical electronics around us. So these come under this umbrella of optoelectronics. So, so to understand optoelectronics, let's take a step back and let's understand uh, what radiations does our sun emit, right? So sun emits everything from infrared to extreme ultraviolet. So we have infrared, we have visible light, then we have ultraviolet, A, B, and C, and then we have far ultraviolet and extreme ultraviolet. So so this helps us understand the broad spectrum of electromagnetic radiations that we interact with. Now, same material, gallium nitride, was previously used to develop these blue light emitting diodes, and these three Japanese gentlemen won the Nobel Prize in physics. So this was back in 2014 for development of blue light emitting diodes. So this was a breakthrough for humanity because the previous technology, the CFL bulbs we were used to use were about 10% efficient. The incumbent technology, which was, let's say, tungsten filament lamps, were like a percent or 2% efficiency. But these LEDs are more than 80% efficient. So this was a significant breakthrough, and because of that, these gentlemen were given Physics Nobel Prize. And I collaborate with Professor Amano, who is in the center here, and it's indeed an honor uh, to collaborate with him. So this was about visible radiation, but what the new technology is in ultraviolet radiation. So if we look at, if we split this ultraviolet radiations into what reaches Earth's surface, then predominantly it consists of UVA, a small portion of UVB, and a negligible UVC, and the radiations below. And this is because the ozone layer above Earth's surface absorbs all these radiations. So that's why this below 280 nanometers, this regime is known as solar blind, because you do not get any radiations from sun on the Earth's surface. So where do these wide bandgap semiconductors come into play? Right? So we saw that gallium nitride has a band gap of 3.4 electron volts. So this translates to a wavelength of 360 nanometers. So this would come here in UVA. And if you change the aluminum mole fraction in this alloy, so if you now alloy gallium nitride and aluminum nitride, so by changing that aluminum mole fraction, you can encompass the entire UV, A, B, and C regime of the electromagnetic spectrum. So what you have the ability to do now is to tune the composition of the semiconductor so as to attain a desired band gap, which would correspond to a specific wavelength. So what we are doing is that we are using this semiconductor now to detect or emit light, as I'll be discussing in just a bit. In the previous segment in power electronics, we were using this band gap block voltage. So it was a different application. In this application, we are basically using the band gap to generate or detect light. So let's say that we make these UVA and UVB detectors, right? So these are exceptionally useful for solar UV monitoring. For instance, if you look at sunlight spectrum, as we discussed, it tails off and then we don't see anything below 290 nanometers. But if you look at the skin sensitivity to these radiations, so these go up as the wavelength goes down, because as the wavelength goes down, the energy of these photons goes up. So each of these photons has a higher energy, and it interacts with our skin uh, significantly as we go below these 300 nanometers. So this is why having ozone layer above us is so critical for human existence. Because if we didn't have that, then everyone would have a skin cancer to start with. So we have been seeing that the ozone layer is depleting every passing day, and this has led to an increasing number of skin cancer cases. So such kind of UV monitors become critically important to monitor the ultraviolet radiation that your skin is getting exposed to. So this is very important. But what we mostly work on is UVC detectors, which are exceptionally useful for applications such as deep UV astronomy, missile plume detection, and so on. For instance, in missile plume detection, I told you that we do not have any background of radiation on the Earth's surface. So when a missile is launched, you can easily detect ultraviolet signature from the missile, because you do not have any big background coming from the sun. So this helps detect the missile rather quickly, and this can be thwarted back by anti-missile technologies. So military has a huge uh, uh, emphasis on this technology. So now let's again talk about how we use these semiconductors in these technologies, right? So if we again see another UV astronomy spectrograph, this was from NASA. in one of their missions. Uh, this is the spectrograph that was used in their mission, and this was based out of silicon technology. So what you see here is that it's a rather bulky unit, and most of it consisted of battery, which because it needed a huge power supply, it needed filters because silicon is not designed to absorb in this deep ultraviolet radiation. So you need a lot of filters. You need to cool the assembly because it absorbs all unwanted radiations. And you also need focusing optics for this to work optimally. So you see that the actual detector module only took like a fraction of weight of the entire spectrograph. So this is not a good technology because your actual detector module is rather small. So what if we could get rid of all these pies and only are left with this gray pie here? So this was our idea, and we wanted to use ultra wide bandgap semiconductors because they don't need any filters and they don't need any focusing optics. And if we could make these self-powered, we can get rid of the battery completely. So we developed these self-powered solar blind detectors where this was engineered to have an electric field in the material, even without applying any external bias. I'll cut the chase and come right to our end result, where we were able to develop about 92% efficiency in these detectors at zero bias. So we don't apply any bias, but the detector is still detecting 92% of photons in this deep ultraviolet radiation. So this remains a world record till date, and we are very excited with this technology development. So again, we could only achieve these results by carefully understanding the material involved, by understanding how defects are controlled in these materials at atomic scales, by doing robust electrical engineering and physics integrated approach. And then the end result was this next generation device technology. So so this was all about UV emission, right? So now let's talk about UV. Sorry, this was all about UV detection. Now let's talk about UV emission. So as I mentioned, moving from gallium nitride to aluminum nitride, you can encompass from 350 to 200 nanometers wavelength. So if we were to make emitters out of these materials, then we can have a range of applications depending on the power and wavelength of the emitted power. So you can have uh, all these you can have non-line of sight communication, you can have quantum computing, you can have water purification, and so on. So there are endless applications for these. And this is what segues me into what I do currently with lit thinking. So lit thinking. So here, this is a brief agenda of what I'm going to talk about in the next 10 minutes or so. So lit thinking is a technology startup where our idea is to enable a safe indoor environment which provides a comfortable, healthy, and safe air for humans to interact. So when we talk about comfortable air, it means it refers to the air in the indoor environment being of a specific temperature, specific relative humidity, and having adequate ventilation. So this means that there are equivalent air changes per hour of a certain number that are happening. And that's why our indoor spaces do need to have regular air conditioning for a comfortable air environment. But what we work on is also providing healthy and safe air. So what healthy air means is that uh, the air quality should promote well-being of the individual and not pose any chronic health risks. For example, if you have any pollutants in the room, so PM 2.5 refers to particulate matter with less than 2.5 micron size particles. We cannot even see these particles, but these are dangerous for humans, and these need to be taken care of. Then we have volatile organic compounds floating in the air. and so on. So these all need to be controlled. And importantly, we need to reduce airborne pathogens, right? We already saw how COVID significantly affected us. So the question is, how can we keep our buildings safe if airborne pathogens are allowed to accumulate in occupied spaces, right? So let's say we habitate a space, like we have a meeting room, and then we have 10 people there, we are going to exhale all these pathogens. So which is obvious when we inhabit the space, but the question is, how can we control the pathogens, and how can we kill these pathogens? So with this view in mind, we our company was started, and so obviously, our big investor is a commercial real estate giant who wanted to use this technology in commercial spaces, because we already saw what pandemic did to us. It decreased our productivity, it increased the operational challenges. There were a lot of economic consequences which we still suffer from. So there's a big demand for disinfecting not just surfaces that we deal with, but the air that we breathe day in and day out. So our solution is to use far UVC light. So UV light with low wavelengths, so close to 220 nanometers. So, so obviously the pandemic taught us a lesson that the indoor environments need to be safe. And right now, it's not safe. So So meaning the effective ways to clean this, and we what we came up with is this filtered far UVC technology that we propose to be using in hospitals, office spaces, government buildings, which would provide constant air disinfection. And so much so that if you use these devices that we have developed, then they offer an order of magnitude higher air changes per hour uh, with just using a small device. So what this means is that you would this is equivalent to changing the air in the room by 180 times in 1 hour. So you are changing the air 3 times every minute. So it's equivalent to that if we use our devices. So we recently launched this device, which has a far UV light source. So it we have done intense research and understanding how it inactivates air-based pathogens. It completely inactivates COVID virus as well. Uh, and we have made these devices to be rather energy efficient. So we have got all the certifications, and actually this device is out in the market to be purchased now. So how does this technology works, right? So 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 it works by inactivating viruses, bacteria, and mold, as I'll be discussing in just a bit. But the idea is that it should do all of this while being safe to humans. So this is what our technology is unique in. Uh, so we have proposed to use this in all these spaces, as I mentioned, and these we have found to be highly effective in all in controlling all these airborne diseases, uh, COVID vaccine, COVID, flu, you have RSVs, common cold. All of these viruses can be completely disinfected by using the technology that we have developed. And this is very critical, right? So in US, there was this study that was done where the absenteeism from COVID uh, costed US as a whole $225 billion, which is crazy, and it was almost like $1,700 per employee was wasted because of COVID during COVID time. So the economic impact of this technology is intense. So So I'll cut through all of these. I just wanted to basically juxtapose the advantages of this technology against all current technologies that are being used. which either require a large time or they are labor intensive at the time being. So with our technology, although the average cost per unit is slightly higher at this point, eventually it's gonna make cost parity is what our calculations tell us. So what is the science behind this far UVC technology, right? So it has been proven that UVC wavelengths, all UVC, let's say below 280 nanometers, are germicidal, which means that it can kill the pathogens, the DNA, RNA of pathogens, the protein elements. So it can just disrupt, damage, and inactivate these viruses. So if you see the plot here, this tells us the DNA protein absorption. The current technology uses this 254 nanometers wavelength, but what we propose is a 222 nanometers based technology, and the idea here is that 222 nanometers wavelength is so intense that it only penetrates till the dead skin. Even in human eye, it doesn't penetrate beyond your tear layer. So what this means is that you can inhabitate the space while this illumination is on from the light source. So this is the game changer technology that we needed for a while now, because the previous technology was such that you will have to empty down the space and then illuminate the space because it will hurt humans. But with this technology, you can inhabitate the space and go about doing your business while this technology is working for you. So we have all these lights actually in our office space, and they are working while we go about doing our work. So it's completely safe to humans, and you can see from these two figures that it doesn't even penetrate the dead skin in our bare skin and the tear layer in our eyes. So, and we have also used a patented filter to filter out harmful radiations so that we only have a narrow 222 nanometer radiation coming out of our device. So obviously this technology is nice and amazing, right? But you saw how big the unit was. So it is still about as big as a normal bulb, but this is because we need all these filters, and there are a lot of elements that go into this technology because this is gas based technology. So we are still arcing a gas which is emitting these ultraviolet radiations, but eventually we would want to make these out of semiconductors, and this is where I come into play because I have an expertise in this domain. So I am helping our company develop an ultra wide bandgap research center, uh, uh, where the research center would be based only on these ultra wide bandgap semiconductors. So we will have everything from materials growth to device fabrication to device characterization. So this would be about uh, $30 million project, about 250 crores rupees project, and we have got the initial uh, funding from our partners. We're very excited about this technology. So the idea would be to use this far UVC regime for sterilization, purification, but it will also open up a lot of these other application spaces as well. So so the current challenge is in this technology is achieving a high quantum efficiency. So essentially, the way LEDs work is that you inject electrons from one end, and you inject holes from one end, and you make these electrons and holes overlap so that you generate a photon through this interaction. So this is how you generate light, but this process can be highly inefficient because of the challenges associated with these materials. And here I plot the experimental data that people have observed uh, as for external quantum efficiency as a function of emission wavelength. So so 400 nanometers is close to blue LEDs, right? So this is what the three Japanese Nobel laureates achieved. a highly efficient blue LED, but as soon as you come down in wavelength, you see that there is a drop in UVA, UVB, and even UVC. All of these are only single digit percent efficient right now. So the technology is far from commercial use, because at least we would need about 10% to make a proper use case of this technology. So there are a lot of challenges in this technology that need to be overcome, and this is what our endeavor is moving forward. So to basically avoid this drop off and make highly efficient far ultraviolet emitters in this range, right? But nitride LEDs are getting better fast, as you can see. Like in the previous few years, the quantum efficiency was below 0.1%, and it has gone up to single digit percentages already. So obviously there is light at the end of tunnel here. So what really limits the efficiency of these LEDs, right? So there are many elements. I'll break it up quickly to the important ones that we are working on. One is that you have defects in the material in this quantum well where you generate the light. You have these point defects that essentially trap down your carriers, and they do not let them recombine to emit light. So because of poor crystal quality, essentially poor quality of the material, you lose out on a lot of efficiency because of this. There are a lot of challenges in injecting carriers into the semiconductor to start with, and there are also challenges in getting light out of the semiconductor. So what happens is that these wide bandgap semiconductors have a huge difference of refractive index with air. So the light just doesn't want to come out of the semiconductor. It rather is reflected back in the semiconductor, and then you only get a, a low fraction of light out of the semiconductor. So these are some fundamental challenges of this technology that we are systematically working on, and eventually we aim to reach the performance of blue LEDs in the deep UV LED technology. So with that, I think I'm running out of time. I'm going to take only 2 minutes to quickly discuss the ultimate future that I foresee of using these materials uh, uh, in this thrust area of quantum information science, which is a rapidly evolving field with the potential to impact multiple technological areas that are not solvable with classical computation power, right? So these would be used in next generation data security or communication technologies. So we hear a lot about quantum computing, quantum encryption, and everything. So for all these technologies to come to light, uh, the control, manipulation, and interrogation of qubits, so which is the quantum equivalent of the classical bit. So this needs to be achieved at room temperature and at large scale. So if you look at quantum computers from IBM or or other companies, these are all huge, but the actual quantum actual qubit element is so small. So you would want this platform to be big, and you would also want this to not to be only used at cryogenic centers, because you cannot use cryogenic facilities everywhere. So we have proposed this new technology where you can make these large scale and you can make these qubits at room temperature. So I'll save the time here by not delving into more details, but I'm very excited if this technology can come to fruition, um, uh, and I think this would be a game changer for the quantum computing endeavor that we all are interested in. All right, so I think with this, I'll summarize my presentation. I hope I convinced you that defects in materials at atomic scales are beautiful to work with. And I hope I also drove across this message that by working at the intersection of different engineering fields is important for the 21st century. So by working at, at the intersection of these fields in an integrated approach can allow to boost the performance of the current technology to the theoretical limit, thus realizing the consummate potential of all these technologies around us and for the technologies to come. So with that, I thank you for your attention and for your time, and I'll be happy to take questions.
Thank you, Dr. Shashwat, for such insightful lecture. The application for FAR UV for air sanitization was a very new concept for all of us, I guess. So we are very thankful for you to make us privy to such a new topic. And I would like to ask the audience if you have any questions.
Thank you. It's my honor.
You can write your question in the chat box as well. If you want mic, please raise the hand. Yeah, I guess the topic was so new that we need some time to have in-depth thought about this topic and come up with few questions so we could contact you after the session as well. So I'm very much
Sure.
thankful
I'll be
from the
open to
organizing
that.
committee of this IFDP. So we could have you for this session. And as a token of respect and love, I would like to give you a virtual memento. The actual physical memento has already been posted and will reach you shortly.
Thank you so
So
much. I
thank you
really
so much
appreciate your invitation.
for this session.
It was a pleasure giving this seminar, and I'll be happy to connect with anyone if they are interested. All right. Have a great day, everyone. Bye bye.
Have a great day to you too. I request all the participants to join for the next session at 2:30.
Sure, we have a couple of questions I see. Okay, shall I answer them? Do we have time?
Yes, you can.
All right, so all right, so
If
I see a
there are any
question.
questions from the audience, you can please write in the chat box. I think I am seeing few
Yes,
questions here. What
yes.
are the applications
So
of these new devices like gallium nitride in power electronics?
yes, so I did mention some of these new applications. Right. In industries, we will see a lot of these gallium nitride based devices to be replacing silicon based, so kilovolt class devices. Then we would see like electric vehicle chargers to be coming out of gallium nitride. So yes, I think all manufacturers have not adopted gallium nitride technology uh, just yet for phones, for laptops, for charging any power electronics. Eventually, if it makes sense, economic sense for adoption, then I think the gallium nitride will penetrate some of these spaces as well. And yes, also in radio frequency electronics, you will see gallium nitride and 6G moving forward. There are already 5G base stations that are based out of gallium nitride. I only covered power electronics, but gallium nitride is exceptionally useful in radio frequency electronics. I'll take the second question, uh, which is asked by Dr. Anaka Chaudhary. Would your proposed device harm outer layer of human skin? So yes, this is a good question. This is what we would normally expect from an ultraviolet light source, that this will harm us. But this is exactly what we have done different. We have used this specific wavelength, which does not penetrate the skin. So it will harm the outer layer of human skin, but that's already dead, so it cannot harm it further. So we always have a dead layer of skin over our actually healthy skin. So it would essentially not make it worse. Um, and also same goes for eyes. There is a tear layer in the eyes that keeps building every uh, uh, every few uh, uh, every few days. So even that doesn't pose any issue to eyes. Um, I think that's about it. I
Are
only
there
see
any
two
other
questions
questions?
here.
I request all the participants to fill their feedback. The link of the feedback form is posted in chat box. So I would like to thank once again Dr. Shashwat Ratkandiwar for giving his valuable time and invaluable insight on these new technologies. Thank you so much, Dr. Shashwat.
Of course, my pleasure.
Have a nice day, sir.
You as well. Thank you.